In this section, we'll study finite difference methods, FDMs. The last section introduced the shooting method for the numerical solution of the linear boundary value problems of this form. This is a second-order differential equation with function values given at edge points in the beginning, and at the end, the function values are given. Now, once the problem is given in this way, here at right edge point, rather than function value, its derivative is given. In this case, the shooting method is hardly applicable. So we'll develop finite difference method for solving such problems in more general environments. Let's begin with recalls. This is Taylor theorem with Lagrange remainder. F is in Cn, which means that the derivatives up to nth derivative continues, and Fn plus 1, which means that n plus first derivative exists. And over the interval, and a point is inside the interval, then for every x in the interval, we have such polynomial, nth the polynomial, plus a remainder term. That is the Taylor theorem with a Lagrange remainder. This can be written in this way. It is an alternative form of Taylor theorem. This is about x0. Now, rather than x0, so here x0 will be replaced by x, and now x will be replaced by x plus h. X is now the base point, and xh is perturbation by h. Then we can write in this way. In detail, we can see here f at x plus h. The perturbed point is now, by using the function values and derivatives, and evaluated at x, we have this polynomial of h, and then remainder part. Okay, that's the one alternative form of the Taylor theorem. We'll use this form and later on. Okay, now here finite difference discretization procedure consists of 4 steps. In the beginning, we'll do partitioning. That means we split the interval, and finite difference approximations. That is for unknown. We will recognize unknowns. And system of differential equations. That means that we try to gather equations of which each equation will give some relation between unknowns. And then from these equations, we try to get algebraic system that is called the assembly. So we have 4 steps. It's quite natural steps. First, we chop the domain, and we recognize the unknown, and we try to get equations showing the relation between the unknowns, and from those equations, we try to get algebraic system. For example, AU equal B. By solving this algebraic system, we can get the solution, approximate solution. Okay, let's begin with step 1, partitioning. We try to partition the interval with equal subintervals. So H is now B minus A over N. So we try to chop the domain from A to B into N equal subintervals here, like that. Okay, so here that is the first one is x0, and next one is x1, and then there will be xn. So there are n subintervals. Okay, let's see this one the same length anyway. And for every function used involved in the equation, now g sub I is g at xi. So for example, yi indicates y at xi. So that is now the partitioning, and this is a notation. And we say that this, the points are the nodal points. So in the beginning, we split the zone, the interval. In the second step, we have to recognize unknowns by using the Taylor series, Taylor formula. We try to recognize the unknowns. Okay, here at xi, now xi plus 1 will be xi plus h, and xi minus 1 is xi minus h. Along with this, we can get yi plus 1 equal, this is alternative form of the Taylor theorem. Okay, we have this, and yi minus 1 is, now we can get, rather than h, we are using minus h. So that here minus h, so that the same positive because squared. And now minus h, then we have here negative, and minus h, that is the same over there. In this way, we can express the value at xi plus 1 and xi minus 1 by using the values at xi. These are Taylor series. And here, to get approximation for y double prime, okay, we have y double prime here and y double prime here. Now we add two equations, then addition, that will be here, and twice of this y at xi, and this first order term will disappear. And then we have twice of this one, and again this will disappear, and twice of this one. So only even order terms will be now here, along with 2, like that. Okay, from this one, we can get y double prime. Just solve the equation for y double prime. We move this into the other side. Everything except this term, and this will be cancelled, and divide by h squared. So move everything else, the other side, and divide by h squared. This one will make minus 2yi here, and divide by h squared. This term will be moved to the other side and divided by h squared. So we have that. Rather than fourth order, we have second order. Similarly, we can get this one. Okay, that is the finite difference formula. Later on, we'll try to use this term only, and we'll ignore these terms. So that is the idea of finite difference method. Recognize the unknowns for y prime, now here we have y prime here. This is y prime, and again here y prime. Rather than adding these two equations, we may try to subtract. Then twice will appear, and this will be eliminated, and eliminated twice of this one, eliminated twice of this one. So let's try to subtract this term from here. Then left hand side will be yi plus 1 minus yi minus 1, and this will disappear, and twice of this one, like that. Exactly, we have this equation. Now we solve the equation for y prime. Move everything to the other side except this term and divide by 2h. Quite simple. Right? So we recheck this equation, and of course we'll try to use this part later on and ignoring these terms. Now this second step is now we try to show unknown and along with finite difference formula. Okay, now in third step, and we have to gather equations, finite difference equations for this differential equation. Okay, for y double prime minus y double prime, here we have minus, there's approximation at xi, and there is xi, and that one. For each point at xi, now we have that. For p, pi, and y prime, we already know this formula, and q at xi, that's q sub I, and y at xi, that's y sub I. And then here, and order for these coefficients, and h squared, and the remaining part will be a fourth order from both sides. You can see for this one, now there's h squared term, h to the 4, and from this one again, h squared term and h to the 4 term, and that can be written in this way. Of course, right hand side, at the same point, you have to get the value. So we have this finite difference equation. And also, and now for every point, it must be defined. So from I equals 0 to n, however here, we don't have to get an equation at x0. x0 is a. Now x0 is a. At a, already we have a value alpha. So that this one must be defined on only the other points from 1 to n. So from 1 to n, we have this equation. Now let's look at the equation at the end. Now here we have, that is b, and this is xn, and this is now xn minus 1. At this point, this equation is defined, and in detail we can see it in this way. And yn minus 1, rather than I, we are using n. So the yn minus 1, yn plus 1 combination. Here again, yn plus 1, and this is okay, and f sub n. However, this yn plus 1 is not defined. So we may consider outside expansion momentarily, so that we have here, there's yn minus 1 is here, now yn is here, yn plus 1 is defined at this point. Now this is a momentary expansion. You cannot deal with yn plus 1 in the algebraic system. So we have to replace this term by using something. But that one is now from the boundary condition. In our boundary condition is this one. At the last point, the slope is beta. Let's try to approximate this equation, and along with these 3 points, xn minus 1, xn, and xn plus 1. Now, this one at xn can be written in this way. Now, yn plus 1, of course, this is representing the y value at xn plus 1 minus yn minus 1. Now, distance is 2h divided by 2h. That is now second order term and fourth order term, and equals beta. That is a standard finite difference, central finite difference scheme for the first order derivative. Okay. So from this one, yn plus 1 can be expressed by using known value, given value, and yn minus 1. You can solve this equation for yn plus 1, and then you can replace yn plus 1 here. Then everything is okay. Such technique is now using ghost grid value. This is ghost grid value, and by using this technique, you can define this finite difference equation well, and yn plus 1 can be replaced in this way. Now, by dropping the remainders, this arrow, that one, this part, and we can get now difference equation. So eventually that is a sort of a second order approximation. So rather than original equation along with y, this is exact value right now. If we consider the error term involved in this equation, then this is exact equation. Rather than exact value, now we try to approximate. So vi is approximation of yi, and by dropping the error terms, then we reach this one the same. Rather than y, we are using v, and we drop the remainder, and we reach this one. And of course, from this one, we have now, okay, we drop this part and multiply 2h and move this one to the other side, then we reach at this one. Okay, and that will now, by using this one, you can replace yn plus 1 when I is n, right? Okay, so here we gathered equations involving the unknowns. That's the end of the third step. Okay, let's go to the last step, step 4, which is assembly. Okay, now we reorganize the equations, and first we multiply, for example, h squared, so that it's easy to handle, and from this one, and then we can get in this way. After multiplying h squared and simplify, then we can reach this equation for I 1 to n. Of course, over there, ci is defined in this way, di is defined in this way. So CI will occupy the sub-diagonal entries, and this is for diagonal, and this is upper, the portion of the diagonal. And of course we are using this one again, and now we gather everything here. And because we know at x0 the value alpha, so by using that we can get this equation. And from 2 to n minus 1, and this interior points, just the standard equation will be used, that equation exactly. And at the end, the last end point, the edge point, now we are using that one, we can get this one. By using these equations, here we can get the algebraic system AV equals B. Now these are coefficients of these V unknowns. And in the beginning, there's 2 plus h squared q1 and minus t1 here. And from 2 to n minus 1, we have minus ci, 2 plus h squared qi, and upper diagonal will be minus di. That is exactly from here to there. And then for the last equation, we have here minus 2 and this quantity. Right? Okay. Now right side, we have contribution from F and contribution from the boundary condition. So here, right side B is, this is from the source term. These two values are from the boundary condition. So we got an algebraic system. That's the end of the assembly. So we finished the 4 steps. Now, once we make this algebraic system, then the solvability is an issue. So we consider now the existence and uniqueness of the finite difference solution. Suppose that PQF are continuous, the functions involved in the differential equation. Now we assume Q is non-negative. And then now CD, the values are positive. Okay, C and D, I'm sorry. And these are involved in this algebraic system. We assume these are positive. Then the linear system, here we can see, and AV equal B. This linear system has unique solution. And that's the theorem. And the reason is here, quite simple. These are chosen such that the matrix is diagonally dominant. And here, and once it is satisfied, then, for example, these are positive, then, and that means that C and D are defined. Just a moment. We defined this one's somewhere, okay, over there. Assume these are positive. Then this addition is basically 2. And absolute value, originally it is positive, and then its addition is 2. So that here, that is diagonally dominant. So it's a 2 plus that 1 and something added so that every diagonally dominant. In fact, this positive condition is not really a little bit, the UK condition can be used in that way. And rather than strictly less than 0, we may consider equality over there. Okay. And along with this condition, we can see easily here the diagonal dominance, and also is quite easily see that and is reducibly diagonally dominant. In fact, because of reducibility, here strict inequality is used. However, even though that is not really given, we can show that it is irreducible. Also, diagonal dominant can be achieved so that once it is okay, then in fact that must be strictly positive. So either way, anyway. Okay, here it is reducibly diagonally dominant, which means that A is non-singular, and therefore the linear system has a unique solution. So we can solve the algebraic system. Okay, the condition in 14.40, that one, Ci, Di are positive. That is the same as, once we are considering L, the maximum value of P in modulus, then that is the same as this condition. So here positive means that in this definition here, there must be positive, so this must be larger, and in negation also, it cannot be less than or equal to 1. That is exactly same as this condition. Also, this is the same as H is less than 2 over L. So here, if we choose H small enough, then always we have unique solution. Okay. Now let's see an example. Use the second order finite difference method to approximate the solution of this problem. X is between 1 and 2, the differentiation. In the beginning, at 1, the function value is 0, and at the right edge point, the function value, the derivative value is minus 2. We rewrite this one in this form, and now then here this q is 1 over x squared and is positive, and then now here p, maximum p, and over 1 between 1 and 2, the value is definitely bounded by 1. So that here, and we have to choose now, okay, and in this way, and if we choose h is now 1 over h, then and 1 over 10, then anyway, here we have that. For this problem, the true solution, exact solution is given in this way. Okay, this one means that here, because we chose h small enough such that with these choices, the algebraic system will be non-singular, and we can get unique solution for each choice. Okay. Here we have a MathTalent program. In this function, we will get here A and B by using PQF. For given PQF, here we are PQF, and AB will be output. Now, after getting the function values, and we define C and D in this way, and then now here we assign and lower, upper, and by using C and D, and the diagonal and right side, and then later on, and either judicial condition and derivative condition, we try to deal with the boundary condition after getting the metric and right hand side B. And in this way, we touch, and this is a left endpoint, and this is a right endpoint. Now this is the main program. We define P, Q, R, and Y. This is the exact solution. And now beginning point value, and this is at right endpoint, the derivative value. And interval is from 1 to 2, and number of interval is 5. Okay. With that, now Y and V over there, that is here cell, and we try to choose 5 degree. Start with a 5, and 10, 20, 40, and 80 sub-intervals. And along with that, we try to refine again to get the solution. Now, for example, here for our case, now boundary condition is 1 and 2. That means that left-hand side is judicial boundary condition, right side is Neumann boundary condition. In PD literature, judicial condition is called the first kind of boundary condition, and derivative condition is called the Neumann condition, which is called the second kind of boundary condition. So for example, if your problem is along with judicial for both sides, then you can assign in this way. Okay. Now, okay, here from 1 to n grid, I is moving that way. Here n is chosen. Now each time refinement start with 5, and now x is chosen, the correspondingly, and PQF is made, and then here after solving, of course this y is the true values. After solving, after calling this function, we have AB and solve it, that is approximate the solution. So for each grid, we get these solutions and save into Y and V. And this remainder part is print out. Okay. Here, for n, when n is 5, the L infinity error is this one. And again, go down. As you can see, here the error is reduced by 4 when the mesh size, grid size reduced by 2. So it is a second order approximation. And you can see error is rapidly go down. And Richardson extrapolation is a numerical procedure in which by using 2 low order solutions, we can get high order solution. And by using these 2 solutions, we can get now 4th order solution. So we have that one. And by using these 2 equations, the solutions, we can get that one. As you can see here, now this Richardson extrapolation has a 4th order. In fact, the error is reduced by a factor of 16, ideally, and go down. We consider this technique early in part 1. You can see details from section 4.2. Anyway, we have this result by using the finite difference method and refinement of the mesh. Let's see some details. And this is now when h is 1 over 5, which means n is 5, and at each point 1.2, 4, and so on. And this is exact solution. This is a numerical solution, and these are error. When h is 1 over 10, which means n is 10. Now we have this is the numeric solution, and this is the error. And now Richardson solution is this one, and that is error. If you compare the error in this column and this column, then you can see mostly, and at every point, is about quarter. This quantity is about quarter over that. So it's a second order, and at every point. Okay. Now here, okay, I guess this is end of the section. Thank you.